So the last talk of the day is from a joint collaboration with Microsoft Azure and UIUC, and it is a paper about about the microservice framework that is offered by Microsoft Azure. And as you can see, that is a long list of authors, but the paper will be presented by Shegufta. He's a PhD student advised by Indy at UIUC, and the title of the talk is Service Fabric, a distributed platform for building microservices in the cloud. And may I ask the AV guy to actually shrink down the screen? Yeah, that would be great. Yeah. All right. All right, let's start.
Okay. Hello everyone. Today I will present our paper on Microsoft Service Fabric. This paper is a collaboration between University of Illinois Urbana-Champaign and Microsoft. Microsoft Service Fabric is a distributed platform for building scalable and reliable microservice-based application. It's a very old project which evolved over more than 15 years. Many production systems, both inside and outside Microsoft, run on top of it. For example, Skype, Cortana, Microsoft Intune, Microsoft IoT Suites, Azure Cosmos DB, BMW, TalkTalk and many more. Microsoft Azure SQL DB, it hosts 2 million DBs containing 3.5 petabyte of data, which spans over 100K machines. Azure Cosmos DB utilizes 2 million cores, which spans over 100K machines, and Microsoft Cloud Telemetry Engine, it processes 3 trillion events per week. So the question is, how did we build such a framework that supports such large scale, consistency, and fault tolerance? In today's presentation, I will try to give you a very brief overview about it. But before jumping into the details, let me show you the high-level picture. This is the diagram of typical monolithic architecture, where this application consists of UI, database, and business logic. In such approach, the DB is typically connected using a cache. There is a load balancer, which in terms of high demand, deploys multiple instances of the entire application. Therefore, it's bulky and it's not cloud-friendly. On the other hand, in microservice-based architecture, the entire applications are divided into smaller components called microservice. There is a microservice manager that deploys this microservice into an array of containers. In case of high demand, this manager deploys more instances of only the necessary microservices. Therefore, it can scale individual components, which makes it more agile and cloud-ready. Our Service Fabric, this is such a microservice orchestrator that allows full lifecycle management for microservice-based application. Some of the goals of the Service Fabric are, it supports strong consistency from ground up way, where higher layers utilizes this lower layers consistency guarantee and they focus on their own notion of consistency. It's fault tolerant and it supports for stateful microservice, where in Service Fabric, each microservice can have their own state. The first two goals are followed by each subsystem, and here are the main subsystem of Microsoft Service Fabric. Due to time constraints, we will only focus on the following 3 major components, where this federation subsystem, this is the core heart of Service Fabric, and on top of it, the reliability subsystem, and top of it, it's the reliable collection. I will mainly focus on the federation subsystem and give you a very brief overview about the other 2. Reliable collection, it's basically a distributed data structure, which similar to a dictionary or queue, that is highly available, fault-tolerant, persistent, and transactional. To ensure these properties, it relies on its immediate lower layer, reliability subsystem, that manages reliable primary selection, consistent replica set, failover management, and replicated state machine. To ensure this, the layer reliability subsystem depends on its immediate lower layer federation subsystem, where this reliable failure detector and routing token forms routing consistency, which in turn solves the leader election problem. Thus, the higher layer benefits from the lower layer exporting their notion of strong consistency. Now, I will briefly cover the federation subsystem. In the federation subsystem, these nodes are organized in a virtual ring consisting of 2 to the power m points. Here, keys are owned by the closest node. Each node maintains a neighborhood, n successor and n predecessor. This ring ensures consistent membership and failure detection, consistent routing, and leader election. This consistent membership and failure detection follows these 2 design principles. The first, here, memberships are always strongly consistent, which means that for each node, all of its monitors agree whether this node is up or down. And it decouples this failure detection from failure decision, which is a really unique way using arbitrator-based approach, which I will cover in my next slide. Here, we are using a lease-based monitoring where 2 nodes, node A and node B, if node A sends a lease request to node B, and node A receives this corresponding acknowledgement, then node B considers this lease as granted. But instead of a one-way lease monitoring, here we are using a symmetric monitoring where both nodes A and B maintains this lease simultaneously and independently. Each of this node maintains this symmetric monitoring with all of its neighbors. And if at least one of these leases fails, that means the failure detection, it asks for an arbitration, that means the decision part. Let's see how this decoupling of detection and decision is done using the arbitrator. But before that, I want to make it clear that for simplicity of this slide, here I am presenting a very simple arbitration scheme consists of a single arbitrator. But in real production, we have multiple arbitrators maintained in a quorum-based approach. For more details, I will ask you to take a look at our paper. So here, 2 nodes, A and B, they failed to renew their lease, this symmetric monitoring. Then, once they detect this failure, immediately they will ask for an arbitration. In this example, say node A's request comes to the arbitrator first. Now, if node A doesn't receive any reply back from the arbitrator within a certain time bound, it will simply go away from the system. On the other hand, if it receives something, it will simply follow the arbitrator's decision. Now let's see how arbitrator decides. For the decision, in this example, arbitrator receives this request from node A first. Therefore, this arbitrator maintains a log where it marks node A as up and node B as down. And it propagates this decision to node A. When node A receives this decision from the arbitrator, it knows that, okay, for sure, within some predefined time bound, node B, even if it's alive, it will not stay in the system. Let's see how is it ensured. Because the symmetric monitoring failed, node B will also detect the failure and it will ask for an arbitration. But the arbitrator already makes some decision about node B. Therefore, arbitrator will immediately reject node B from the system. Thus, decoupling this detection from decision ensures consistent failure detection. In our ring, this, unlike other P2P distributed hash tables, the service ring maintains both clockwise and anti-clockwise routing entries. In SF routing, it provides more routing option. It routes messages faster. But before that, let me clear it. In the latest design, this SF routing only used for bootstrapping and discovering routing when a node starts up. After this discovery, node can communicate directly. This SF ring ensures consistent routing, which ensures that at any given time, all messages sent to key K will be received by an unique node. If that node crashes, a new node will come up and take that responsibility. This consistent routing provides implicit leader election. For example, in the entire system, the node that owns the key for K equals to 0 is the leader. To ensure this, here each node owns a routing token, which is a portion of the ring whose key it's responsible for. SF ring ensures this following consistency property for routing token. The first, it's always safe. There is no overlap among this token owned by nodes. And eventually every token range will be claimed by a node. It can also efficiently handle node join, leave, and fail protocol. We haven't explained it in our paper. Now, this service SF ring, it's being used for production for more than 15 years, and it's working successfully. So hence, we haven't had to change it. But it was invented concurrent with cord and pastry. But note that cord, pastry, they do not support strong consistency. Now, I will give a very brief overview of the reliability subsystem. The reliability subsystem provides replication, high availability, load balancing. The consistent lower layer, that means the federation subsystem, helps reliability subsystem to easily implement these guarantees. Next, I will very briefly introduce the reliable collection. Reliable collection is Service Fabric's distributed data structure that is fault-tolerant, highly available, persistent, and transactional. It leverages this lower layer guarantee, which is the main goal of the Service Fabric, and like failure detection, leader election, and load balance, etc. It is used in stateful microservice. Now, I will jump to the evaluation part. Here, we evaluate our Service Fabric's arbitrator-based approach with an arbitrator-less approach, where if a node fails to maintain lease, it will gracefully leave the system. It is a fully distributed way of maintaining strong consistency. In both of this case, we varied this total number of neighbors. In this experiment, we deployed 2 rings, consist of 64 nodes, and then selected few nodes and intentionally crashes them. The x-axis shows the node ID that were crashed, and in the y-axis, it shows that what is the total number of node that was finally forced to leave from the system. We can see that our arbitrator-based scheme, with high accuracy, it can always detect the exact number of nodes. When we crash 4 nodes, only those 4 nodes were forced to leave the system. On the other hand, in arbitrator-less scheme, say when the total number of neighbors is 4, when we crash node 1, this node 1, along with all its 4 neighbors, that means total 5 nodes, were forced to leave the system. And this number increases when the number of failed node increases. So therefore, it is prone to cascading failure. There are some scalable failure detectors, which are not similar to SWIM, which are not strong. There are also some strong failure detectors, like virtual synchrony, which are not scalable. But our arbitrator-based failure detector, it is scalable. It is a strong failure detector. It prevents cascading failure, and it doesn't depend on the total number of neighbors. Next, we analyze this reconfiguration event, where we collected total 20 days of reconfiguration traces. We classify this event into 3 categories: failover, swap primary, and other, for example, swap secondary. Note that only the first 2 affects this availability. Next, in the graph below, we measure the reconfiguration delay taken by each category. Typically, the cost of strong consistency is high latency, but as you can see, Service Fabric scheduling latency is typically in a couple of seconds. But to make it clear that currently it is dramatically optimized to 100 of milliseconds. Now, I will give a summary of all of our evaluation. For details, please take a look at the paper. Our arbitrator-based strong failure detector, it is scalable. It has minimum failure detection overhead. It prevents cascading failure. It uses less arbitration meshes compared to our arbitration-less scheme. It doesn't get affected by the total number of neighbors. Our reconfiguration, here, control decisions are generated quickly within 1 to 2 seconds, and our Service Fabric's current reactive reconfiguration approach is ensuring availability for 10 million microservices. In terms of message delay, even in the presence of higher churn, message delay remains largely unaffected. And our SF routing, it ensures higher, even though it requires higher memory than cord, but here message takes fewer hops. As a result, here routing are faster. In summary, I have presented Service Fabric, a distributed platform that enables building and management of scalable and reliable microservice-based application. I have also presented how Service Fabric ensures strong consistency and fault tolerance from lower layer, which helps us to build state in the upper layer. And I have briefly covered 3 core components of Service Fabric: federation subsystem, reliability subsystem, and reliable collections. The Service Fabric code is now open source, and you can check it from the GitHub link. So this was a brief presentation about this paper, and I'll love to take any questions.
All right, thanks the speaker. Great talk. So we have time for questions now. Yeah, there is one in the back.
Hi, hello. So could you elaborate a little bit of what happens when the arbitrators fail? What is the behavior?
Sure, that's a really nice question. So, as I said that in our case, okay, you give me a scope to explain more in this slide. This arbitrator, in real system, there are multiple arbitrators. Say there are 5 arbitrators or 11 arbitrators or number of arbitrators. Then these nodes are parallelly sending this arbitration request to all the arbitrators. And then the arbitrator makes independent decision. Say for example, node A, there are 11 arbitrators. Node A sends this arbitration request, and node B sends this arbitration request. Node A receives 6 alive response, and node B receives 5 dead response. Now, as the quorum is on node A's side, node A will stay in the system, and node B has to leave the system. Now, the question is, what if arbitrator is dead? Because of multiple arbitration, it's fault tolerant, but if the quorum number of arbitration is dead, yes, that's true. In that case, if there is if any node fails, it will try to communicate with this arbitrator. It won't be able to make this quorum, therefore, it will leave the system. So actually, yeah, in that case, the entire ring will die. But that's a really exceptional case in our scenario.
So let me do a follow-up, which is, so if all the nodes need to send a message to all the arbitrators,
okay.
If that's the case, how is the system scalable with the number of nodes?
Okay, the interesting part is that here, nodes are communicating with this arbitrator only when they detect the failure. So it is a really rare case where all the nodes detect failure as each other and they will send this arbitrator. Yeah, if that somehow happens, in that case, this arbitrator will be congested. But actually, the design is we have implemented in such a way that it's extremely rare incident.
Thank you.
You reported the latency right here. You reported the latency for various recovery operations. Has anyone taken a look at how those affect service level objectives for the higher level microservices built on top of this?
Sorry, can you please repeat?
How do these operations affect service level objectives for the microservices built on top of this?
Okay, so here, this is the latency, this is the end-to-end latency. So if a microservice fails, if a secondary service fails, then it can always communicate with the primary and it can read this data. But if a primary fails, or if because of this congestion, if you need to swap the primary to another place, in that case, there is a slight amount of unavailability period. But yeah, the end-to-end unavailability period is from 1 to 2 seconds in all of these cases.
All right, more questions? If not, then let's thank the speaker one more time.